Okay, hello folks. Welcome to another week of Offsite Learning. This week we move into chapter 14, okay? So you'll need the new notes. They're posted in the Google Classroom and also in the agenda. They look like this. Again, I'll just say it at the top. Make sure, guys, you're coming to me with any questions. Of course, you can come to Flex, but you can also just send me an email anytime or put a question in that Flex Google Doc, and then I can answer it whenever. And with that, let's jump into chapter 14. So we begin chapter 14 thinking a little bit ahead to where we are going to be in Unit D, which is looking at models of the atom. To really understand where we're going to go then, we have to begin here with kind of the birth of quantum, which you learned in Science 10 as the kind of current model of the atom, all right? So what does that all mean? We're going to kind of build the story along as we go through chapter 14 and rewrite a lot of the physics that you come to understand in the last couple years here. So the story of the development of quantum theory begins with a scientist named Max Planck. Yes, Planck, okay? It looks like Planck, it's pronounced Planck. So Planck was studying something called blackbody radiation. What is blackbody radiation? Well, hot objects glow. You may have seen this, right? If you're making toast, you look inside the toaster, the little filaments, they heat up and they get red hot, right? Or an old incandescent light bulb, not the fluorescent ones like we have, but an incandescent one. How does it work? Well, electrons flow through there, there's resistance, the filament heats up, and it heats up enough that it actually becomes white hot. And so the higher the temperature is of the object, the shorter the wavelength of the light that it emits, right? So even the saying red hot versus white hot, right? Red hot is pretty hot, but we know that white hot is even hotter. Why do you never see things that are green hot? Well, as it gets hotter and hotter, it's still emitting that red and they all start to combine. And then that's why we get white hot. When all of those wavelengths are combined, you get white light. As we know, all colors put together makes white light. So white hot is kind of the hottest. Of course, it gets hotter than that. You could have something that's emitting UV ray, like our sun, right? Our sun emits a lot of UV. So just stepping back a bit here, why does it make sense that hot objects even emit radiation in the first place? Well, use your knowledge of the particle model of matter and our knowledge of physics 30 of how EMR is produced. Particle model of matter, when something was heating up, what was happening to its particles? They were moving faster and faster, right? They were jiggling quicker and quicker. And hey, particles are made of charges. Protons are charges, electrons are charges. So we have these wiggling charges. Wiggling is accelerating. So we have accelerating charges. So the hotter they are, the faster they're jiggling. And hey, the faster they're jiggling, the greater the frequency of the EMR they're producing. So thermal energy is really just the kinetic energy of those particles jiggling, right? That's why when you melt something to take it from a solid to a liquid, you make its particles jiggle faster and faster until they kind of break apart into a liquid. And then keep doing that and they break even further apart. They get even more kinetic energy and become a gas. Right? And as they jiggle, they are charges, and so they jiggle and accelerate and produce EMR. All right, so physicists were really interested in this relationship between the object's temperature and the radiation it produced. So they came up with this hypothetical object, doesn't really exist, but we can approximate a lot of objects as these things, and it's called a black body. So a black body perfectly absorbs all radiation incident upon it because black things absorb all light, right? White things reflect all light, black things absorb all light. Black bodies are even better than that. They absorb all types of EMR, down to gamma ray and up to radiation. They perfectly absorb it all. And then they become perfect re-emitters. So they perfectly re-emit it all until they reach something called thermal equilibrium, which just means they're the same temperature as their environments, right? That just follows the second law of thermodynamics. Energy goes from high to low. Heat flows from high to low. So black bodies, perfect absorbers, and then perfect re-emitters. So as it heats up, because it's absorbing that energy, its emitted EMR will also increase. The wavelength will decrease. And so that's why we get things as they get hotter going from, well, not glowing. You and I, we don't glow. We mostly emit in the infrared, right? But if you look at your toaster or a fire poker in the fire, right, it glows red. It eventually gets enough energy that it starts to glow in the visible range. And it can keep going to the ultraviolet or on and on. So what you're looking at here is a few experimental curves that we deduced for things at different temperatures. So at 6,000 Kelvin, that's about the temperature of the sun. You see, this is what the curve looks like for energy radiated versus the wavelength of the light, right? Notice the sun peaks here, hey, right in the middle of the visible light range. Any guesses why our eyes evolved to see visible light? No mystery now, right? Our eyes evolved to see visible light and not UV light or infrared light because our star's emissions peak in the visible spectrum. So you can see kind of on a simulation here, right? Here's a blackbody curve. So notice, right, as I go to the temperature of, say, right there, see it's peaking kind of in the infrared, slightly larger than the red wavelengths. That's probably like the temperature of you or me, right? I get to a light bulb. It's now hot enough. As we know, light bulbs are very hot, but it's now hot enough that it is starting to emit some visible light here. We can kind of see the temperature, what it would look like here. That's kind of what this is simulating, right? As we go up, as we go up, as we go up, I'll have to zoom out on the graph here, okay? So that curve didn't just get smaller. I just zoomed out. Right now we've reached the temperature of the sun. It's glowing kind of white hot because it's emitting all wavelengths of the visible spectrum and they're combining together into white light, right? There are stars much hotter than our sun. We can go up to Sirius A, one of the hotter stars in our universe. Notice, and Sirius A, if you look at it, it's actually blue, right? It actually appears blue. Why isn't it still just white? Well, because notice the red has really dropped off. The blue and the violet are, there's a lot more under the curve there. In fact, it peaks in the UV. If we lived near Sirius A, we'd be cooked pretty quick by UV radiation. In fact, you can see it's even probably starting to get a decent amount of X-rays put out. So when we look out in this and we see X-rays, we know we're looking at something pretty hot or pretty high energy, right? Now, again, this is the experimental curve. This is what our observations told us was happening. But I've kind of waved over something major here, something major in the world of physics that had to do with that exact blackbody curve we were just looking at. So a couple of scientists, Lord Rayleigh, William Jeans, came up with an equation that modeled the intensity of light as a function of wavelength for a black body with a given temperature. And they did it using all of our classical physics. They had Maxwell's theories in there. They were using Young's double slit. All of the culmination of the hundreds of years of classical physics went into this equation. And they were trying to see the intensity of light as a function of wavelength. Intensity, what does that word mean? Intensity refers to the amount of light energy leaving or incident upon an area every second. So to kind of visualize that, what does it look like? We have some square area, right? 1 meter squared. This is what high intensity would look like. Okay, a lot of light incident upon some area. Now we could have the light of the exact same wavelength, but at a lower intensity. Same 1 meter squared, low intensity would look something like less energy per second per unit area. Okay, so intensity is actually in units of power per given area. Okay, power, as we know, is just energy per time per unit area, right? So essentially, every second, how much energy is flowing through this unit area. And so Rayleigh and Jeans came up with this equation. It incorporated all the classic physics we looked at. And their equation worked really well for large wavelength, low frequency radiation. Okay, it really did. When we looked at something and said, okay, how many radio waves or how many microwaves or even how many infrared rays is it emitting? It worked pretty well. It said, yeah, their equation agreed very well with theory. The predictions of the classical physics in the equation worked out great. However, around the ultraviolet wavelengths and smaller, the predictions started to diverge hugely from what we saw. Okay, so you can see that here on the graph. This is what the Rayleigh-Jeans law and all of the classical physics that went into it predicted. And again, this is what we saw. It peaked and then it dropped back off. Now, even worse than that, even worse than the fact that it didn't match our observations, which that alone is enough to kind of say something's wrong here. Something's really wrong with all of the physics we've been doing. Even worse, it predicted that any object with some amount of thermal energy should be radiating an infinite amount of light energy. In other words, anything that's not at absolute zero would fill the universe with huge bursts of gamma rays, and you making your toast in the morning would incinerate the observable universe, right? Obviously, that doesn't happen. Something is wrong here. Something is very wrong. We called it the ultraviolet catastrophe because those are the wavelengths that it started to really mess up at, right? It was fine for the lower wavelengths, but once you hit UV, something started to go wrong. And it really was a catastrophe, okay? It meant there was something fundamentally wrong with all of the physics that went into the Rayleigh-Jeans equations. And what physics went into the Rayleigh-Jeans equations? Well, everything you've learned, okay? So everything you've learned up until now is known as classical physics. Today, with the ultraviolet catastrophe, we move into quantum physics, which is part of modern physics. We split physics into classical and modern. This is how much of a shift we're about to do here. This is how important these discoveries were. So what was the problem with the Rayleigh-Jeans law? Well, they assumed that the particles could and would vibrate with any frequency, okay, and therefore emit any frequency of EMR. This was something known as equipartition theory, which was kind of fundamental to our understanding of thermodynamics. Now, if there's an infinite number of ways to be vibrating and radiating EMR, and they're all happening, well, then there should be an infinite amount of energy radiating from any blackbody, right? Right? If it is doing all of them, then it's doing an infinite number of vibrations and therefore emitting an infinite amount of radiation. But that's how waves work. They are continuous. They do emit. You can have any frequency, right? You name some frequency. I'll say, well, you could have half of that. You could have a quarter of that. You could have 1/256th of that. Name a frequency that I can't do that for. You can't. And then Planck tried something sort of crazy, okay? To address it, he tried something in what he called a moment of desperation. Those are his own words. Planck proposed that there was a minimum and indivisible amount of energy that a particular frequency of EMR can transfer to the matter it interacts with. A minimum piece of energy. He called this little piece of energy a quantum. And more than one quantum is quanta. What he was doing was saying, okay, maybe it can't have any old frequency. There is a discrete amount, a minimum possible energy that you can't say, well, it could have half of that. What he's saying is that there is some frequency you could come up with that I can't realistically say, well, what about half of that? Okay. All energies were not permitted. There could be no such thing as half of a quantum for a given frequency. That was the minimum amount it could take. Now, when Planck did this, when he made that assumption and came up with an equation based on it, the equation modeled the blackbody observations perfectly, like scary perfectly. It was bang on. But even Planck didn't think these quanta were real, okay? This was a Hail Mary. He was just trying something to make the math work. So much of physics is playing around with math. And so Planck was getting the math to work, but even he said, this is obviously fake, guys. I don't know why, but it just makes the math work. And for this little weird math trick that he tried, with this weird little math trick that Planck tried, he had stumbled on to one of the most revolutionary ideas in physics. It literally completely revolutionized the way that we look at the workings of our universe. So what did Planck do? Now, this is not Planck's equation for the black body. That is much more complicated than this. But this is the assumption that he kind of made at the beginning, right? So E is the total energy of the light. E is the energy carried by the light. H is Planck's constant. It's just a proportionality constant. So he said there's some minimum energy any frequency of light can carry, and that energy is the frequency times some very, very small number. And then experimentally, they went and found the number and found it to be, yes, indeed, it was very small. It was 6.63 times 10 to the negative 34 joule seconds. That's on the back of your formula sheet. Again, remember G, the gravitational constant. Remember K, Coulomb's constant. These are fundamental constants cooked into the code of our universe. Planck's constant is one such constant. In fact, it might be the most prevalent. It pops up in so many places, it's not even funny, okay? F, of course, is still the frequency. C is the speed of light in a vacuum. I'm just going to add to this NHF, but since F is C over lambda, we could also say NHC over lambda. A lambda is still the wavelength. And here's the weird part. N is a whole number. It's 1, it's 2, it's 3, it's 4. It's never 1.5, it's never 1.75, it's never 0.5. Do you hear what we're saying here, right? Energy in light is quantized. There's some minimum amount. You can't just divide that by 2. It is not continuous. There is some minimum amount. Weird, really weird. And like I said, Planck didn't think it was real. It just made the math work. So one quantum of energy would have a energy of HF, right? 2 quanta would have 2HF. 3 quanta would have 3HF. These little quanta of energy, these little packets of energy, he called them, okay? So not all energy are possible. Nothing could ever have half a quanta of energy. So what's the big deal? Well, we'll get there, but waves can transfer continuous amounts of energy, right? Continuous means infinitely divisible. So you say 1, and I can imagine 0.1, 0.2, 0.3, 0.0006, 0.247, right? Those are all fine. for a continuous quantity. So waves can just keep transmitting energy, right? Of course, a wave can transmit to you energy anywhere from 0 joules to 1 joules and literally everything in between. Particles, however, they transfer their energy or they don't. They do it in discrete amounts. So if I throw a baseball at you, right, the baseball hits you and it transfers its energy to you. Okay, it's all at once. It just happens. And so are we saying that n here is the number of particles of light? Well, sort of. Okay, we'll come back to it, but they're not particles. They're not little balls with massive light. We think of them as little individual packets of wave energy, okay, that do act like a particle in that it transfers energy in discrete amounts. So some introductory terms here, okay, some definitions we need to get out of the way. So just the idea of a quantized quantity, it's one that's made up of fundamental minimum parts, okay? So for example, money, right? What's the smallest unit of money? Cents. Can you have half a cent? No, right? Or like a population. A population is made up of many individuals, but it's quantized into those individuals. You can't have half an individual be part of a population. Now, it was the chemist Gilbert Lewis that came up with the name, and he was just trying to put a name on this weird kind of thing. Planck said, okay, I don't know about this, but let's just call these little weird packets of energy. Let's call them photons, okay? Photo being the root for light, right? A photograph is a light capturing device. So we need to describe the quantized nature of light. We refer to it in the context of photons. So a beam of light is made up of photons, just like a dollar is made up of cents. You can't have half a photon. At least that's what Planck's equation seems to be suggesting. All right. When you're calculating, you must use joules unless it's a very specific type of question where you've been very careful and checked and you can use this other unit. 9 times out of 10, you'll need to use joules. Why? Because Planck's constant is in joule seconds, not electron volt seconds. Well, what's an electron volt? Glad you asked. Energies in this unit can be very, very small. So sometimes it's more convenient to use a very small unit of energy called an electron volt. What is an electron volt? It's 1.6 times 10 to the negative 19 joules. You might be saying to yourself, I recognize that number. That's the charge of an electron. And you're absolutely right. That's not a weird coincidence. It comes from how we define an electron volt. It's the amount of energy it would take to move something with the elementary charge E through a potential difference of 1 volt. Good chance to remind ourselves of the equation here, right? So the amount of energy in electron volts, if you have the charge of 1 electron, 1.6 times 10 to the negative 19 coulombs, and you're moving it through a potential difference of 1 volt, of course, an electron volt then is defined as 1.6 times 10 to the negative 19 joules. So I'll do this one example here, okay? And then again, I'm going to make another video with the examples that follow. So this again is just going to be the theory video, but I will throw in this one example here at the end because it's a good way to just bring it home, okay? So what is the energy of a red light photon? Remember, photon is just the word for this little packet of energy that we're kind of weirdly, to make the math work, assuming exists right now, okay? That has a wavelength of 654 nanometers. So that is the wavelength. And then we're going to find an electron volts too. So yes, E equals NHF, right? But for this one, how many photons are we talking about here? How many quanta? Just one, right? So for the most part here in Physics 30, not always, but for the most part, N will be 1. In fact, if you look on your formula sheet, you will see that they don't even give you NHF. They just say E equals HF. But you have to know that this is the energy per photon, okay? So for this one, since we're dealing with one photon, we can just say E equals hc over lambda. H being the very, very small Planck's constant times 10 to the negative 34, right? Speed of light. And I got the energy of this quanta. How much is stored in this little packet of energy is not a lot, but it's one little packet of energy in a beam of light. Now in electron volts, just like when we're converting any other unit, take your answer. Should probably be using more sig digs, my bad. So just a unit conversion here, right? Because electron volts are just a unit of energy. We're just changing from joules over to those. Okay, so I want electron volts, and I need to know how many electron volts in a joule, right? Well, 1 electron volt is 1.60 times 10 to the negative 19 joules, right? A very small amount of joules in 1 electron volt. By the way, you can check the back of your formula sheet for that conversion rate, okay? That is on there. So double check quickly that my units work out. Yep, joules cancel, And I got that many joules, that very small amount of joules is 1.90 electron volts. So you can kind of see these numbers are definitely more convenient to work with when we're talking about these very tiny amounts of energy, right? That's where the electron volt comes in handy, really. Okay, so I'm going to wrap up the theory video there. I will do a video doing the examples on the following pages. I recommend maybe going and trying them out on your own, and if you get stuck, maybe go watch the example video, okay? Or if you just want a deeper explanation, you can go straight into that. Whatever floats your boat. And if you're looking for practice with this, check the Google Classroom or the agenda for the questions that go with this topic.